Okay, this is a quick video going over partial fraction decomposition with an example to follow. The key for starting partial fraction decomposition is that the degree of the denominator must be greater than the degree of the numerator, strictly greater than. If it's the other way around, where it's less than, or even if it's equal, you can't start partial fraction decomposition. Okay? The process to start it then would it be that you have to do some algebra, some long division in order to get it into the format where denominator degree is more than numerator degree. But anyway, once you have it in the form, here's the idea. We have a numerator p of x and a denominator q of x. These are polynomials, and this is built for being able to integrate such functions, partial fraction decomposition. This slide is talking about how to decompose. The next slide will be us using that decomposition on an example. So decomposing the fraction who is all together in one fraction, decomposing it is breaking it into smaller fractions. So here's how it works. If your numerator and denominator, which together make what's called a rational function, if you focus in on your denominator and you recognize the type of term that it has, that then dictates to you how to decompose it. Let's focus on the q of x, the denominator. If it has only linear polynomials, like x minus 4 and 2x plus 3, if it only has those guys, then each one gets its own fraction with that guy as the denominator. You see, what we're doing is we're going to put in constants in the numerator. How could this one fraction be put together from these two separate fractions? That's our goal. We're going to have to be able to find out what kind of constants make this happen. And so the x minus 4 brings in this fraction, and then the 2x plus 3 brings in this fraction. Everybody gets their own fraction, and it's quite simple when there are only linear polynomials in the denominator, or if there's a linear factor in the denominator, then it gets its own fraction. Okay. Now, what if there are linear factors that are raised to powers? Here's an example of one of those. We have x minus 3 who is squared. Oh, no, sorry, cubed. X minus 3 is cubed. The decomposition just changes drastically. You see, you don't just get a fraction for x minus 3 cubed. No, you actually need a fraction for every power that's underneath that as well. So we're going to need a fraction for the square. We're going to need a fraction for the term to the first power. This one part of the denominator gives us 3 separate fractions. It's possible that it can be decomposed. It might not, each one of these guys might not be, something that's not, one of them might be 0, but the point is, though, that we decompose the one fraction for every power. And the numerators, they're just constants, okay? What this other guy here is just the other linear factor. So we have a linear factor here, x plus 5, it gets its own d over x plus 5. Okay, the order doesn't matter, you can rearrange them, okay? But I just want you to know this is 2 very separate decompositions. Linear, one fraction. Linear, that's raised to a power, that many fractions based on the power. The last type of term that can show up in the denominator is an irreducible quadratic. When you have one of those, the decomposition is further, and it's further the fact that it's different. What's different so much about it is the numerator. Here's our quadratic, which is irreducible. An irreducible quadratic has no real roots. The roots are imaginary. B squared minus 4ac is less than 0 when you throw it into the quadratic formula. This is a case of that, x squared plus 2x plus 10. So the fraction that comes from that, it gets its own fraction, but what's so very, very different is the numerator. Then and only then does your numerator turn into something that's not a single constant. The numerator is ax plus b. If it was further down the line, bx plus c. Basically, the numerator is linear. Denominator is this irreducible quadratic. Numerator is linear. It's two different constants. There's an a and a b. Okay, the other guy that's there, that's just your standard linear factor who has its own separate fraction. Okay, I guess there could be one more type. It could be an irreducible quadratic that's raised to a power, but let's not consider that. Okay, so this is it. Identify correctly what type of term you have in your denominator, and that will dictate to you your decomposition. And then it's an algebra game. Your job, chase down those constants that will allow you to break apart the fraction. And the way that's done basically is trying to put the fraction back together, multiplying by the parts of the denominator that you're missing. Okay, here's our example. This comes from one of my friends. She's taking a class at a local university, and she says, I need help with this question. I just, the decomposition is troublesome for me, so this one's for you. It's x squared plus 9x plus 2 in the numerator, and the denominator is x minus 1 quantity squared and x plus 3. So, first check, is the degree of the denominator more than the degree of the numerator? Don't be deceived. The denominator degree is not a 2 just because you see a little 2 exponent there. Imagine that's a quadratic, but it's multiplied by a linear. When you multiply it all out, it's going to be a cubic in the denominator. So yes, the degree of the denominator is 3. The degree of the numerator is 2. You're good. You can start the process. All right. So what's the process? Zero in on the denominator. All your attention is there. Correctly identify what these terms are. The x minus 1 quantity squared, that is a linear who's raised to a power. The x plus 3, it's just a linear. So then how do they decompose? They decompose in the following manner. You get one power for every power that's there. You get one fraction for every power that's there in that linear that's raised to a power. For the linear, you just get one fraction. So I put that first. I put the linear part first. And then I have my linear who's raised to a power giving me 2 fractions. My one fraction is the term itself, x minus 1 quantity squared. But then I got to go down in power and then just have x minus 1. I didn't put parentheses around it, but it is these two, let me highlight again. It is these 2 fractions that are coming from the fact that this one term is in the denominator. But notice all the numerators, they're just constants, okay? Don't even think about trying to use an irreducible quadratic. No, a linear ax plus b or something up top, not necessary. That only happens when there's an irreducible quadratic. Okay, now it's our job to chase down the ABC. How do we do it? Imagine trying to put the fractions back together. You have 3 fractions, you want to put them into one fraction. It's all about having this common denominator. Well, what's your common denominator? It's the same denominator you started with. That's your common denominator. So that's the guy you have to get to. How do you get to that guy? You multiply by what you're missing. And so the first fraction, my common denominator is in highlighted yellow there. What is it missing from there? It's missing an x minus 1 squared. You should multiply top and bottom by that. My second guy has an x minus 1 squared. It's missing the x plus 3. You multiply top and bottom by that. Be careful about the third fraction. This is the one that gives students fits. You're trying to get the common denominator of x minus 1 quantity squared times x plus 3. You only have one factor of x minus 1, so you need another factor of x minus 1, and you're going to need the x plus 3. That's the one that students really mess up. The other ones, students are fine. They say, oh, I have this one term, I need the other term. I have this one term, I need the other term. So that's fine. They don't struggle there. Students struggle with the trying to figure out how to work when there is this extra fraction that we have, and here's how it's going to be brought into the common denominator. Okay? All right, great. Let me erase all these highlighters. Here we go. And it's supposed to be equal to the original fraction. That's what's on the right-hand side there. What do you do once you have the common denominator? Well, you then focus all of your attention on the numerators, basically. You're going to put them all together. On the left-hand side, that numerator, the new, would be all these guys added together. We have the A who's times the x minus 1 squared, the B who's times the x plus 3, the C who's times both the x plus 3 and the x minus 1, and then it's going to be equal to the right-hand side's numerator. This is our equation. It governs the finding of the constants A, B, and C. Now, after you do a few of these, you'll be able to skip to this equation. Like you wouldn't have to write that intermediate step of putting, putting them all underneath the same denominator. But when you skip steps, sometimes you make mistakes though. So I recommend putting it in there. But here we go. This equation is true for all x, okay? One approach to this, the standard historical approach, is just to multiply out the left-hand side, look at the right-hand side, match up coefficients. If you got a squared term on the left, then the coefficient on the squared term on the right should be equal to that. And so, and the same thing for the x's and the constants. I don't prefer to use that method. So I guess the method that I like to use would be considered a shortcut to that. My method is to, since this is true for all x whatsoever, I'm going to be very smart about it. I'm going to pick an x that will eliminate most of the equation, leave me with something simpler to solve. You see, the x's that originally make your denominator 0, 1, and -3, they are the guys you want to use to plug in here. Watch what happens when you plug in a -3 first, and then we'll plug a 1 in later. If I plug a -3 in, every place I see an x, it looks like a mess, okay? But look what happens to the term that has B on it and the term that has C on it. Plugging -3 in there puts a 0 on that term. I don't have to worry about B or C because they're multiplied by 0. So all I have to worry about then is just A. And so picking x equals -3 is strategic because of these factors of x plus 3 here will help us to zero out those two terms. Okay, all right, great. What are you left with? The A term has a -4 who is squared, so 16A. And the right-hand side, square the -3, you get a 9, you get a -27, and you get a +2. The right-hand side, 11 take away 27 is a -16. So there we have it. A is a 1. I'm sorry, A is a -1. And we're making our way through this algebra minefield, but we're using it, we're being really smart about it. Okay. We've chosen x equals -3, and it was fruitful. The next choice is x equals 1. It'll be fruitful. Because the terms that have an x minus 1 factor, they get zeroed out. And we'll be able to solve for the B term. See, these guys, they're gone. They're not there. They're gone. 1 minus 1, they have a 0 on them. Okay? So they're gone. Who's left? The B term, 4B. And then we have the right-hand side, 1 and 9 and 2. So that's good. 4B is 12. Come on now, B is 3. We're doing great. Now here's where we reach a little impasse. That was wonderful. It killed all the variables. We're great. Well, then we try to pick something else. But what else? Something else. And we've chosen all of our smart choices. -1 and +1 and -3. They're gone. We've chosen those guys. There's nothing else that's going to eliminate everybody like we did before. And so at this point, then our smart choices are gone. Now we gotta just pick something convenient. Okay. And then we use the fact that we know A and B already. So then we'll be able to get what C is. That's all. Okay. Something really convenient to plug in is 0. I would love plugging in 0. Somebody asked me to plug in something, it's going to be 0. Okay. That's the thing I love to plug in. It kills, especially to polynomials. Oh my gosh. The right-hand side is automatically going to be simple. It's going to be 2. I can look at the right-hand side and know when I plug a 0 in, I get a 2 out. Okay, so here we go. We're going to plug a 0 in. All right, and it's just a convenient choice. Run out of smart choices, you go with convenient choices. All right, so no variable gets eliminated, but that's okay. We know 2 of the variables already. We know that A is -1. We know that B is 3. And so then we end up with an equation that just has a C in it after we plug those guys in. Okay, here we go. So we have a -1 plus a 9. And then the C term, who is a -3C? Yeah, right-hand side equals to 2. Take that 8, move it over, subtract it, and then that's a -6, and then divide by the -3 to get a 2. Ooh, 2 plus 2. Okay, that's a typo on my part. Sorry about that. It's a 2, positive 2. Okay. All right, great. So we've done it. We've chased down the constants. Usually the problem, isn't just to do that though. There's some calculus. That's just an algebra question so far. Where's the calculus at? The calculus is then to integrate this. All right. The goal is to be able to integrate. You have this function trying to find the antiderivative of, and through this algebra, 80–90% algebra, this question is, we're able to get simpler fractions. We decomposed partial fraction decomposition. We decomposed into simpler fractions, and we can integrate these guys. These are nice. When I say simple, I mean like easy to integrate. I mean, the antiderivative of 1 over x plus a is just going to be natural log of x plus a, technically with absolute value bars. I didn't put the plus c on the second guy, but the antiderivative of 1 over x plus a quantity squared is -1 over x plus a. If you need to see those done, just work a little u sub, you'll see it. And so in no time flat, we can just read off the answer by putting the coefficients in front of these guys. We'll have a -1 natural log of x plus 3. We'll have a -3 on top of x minus 1. And then we'll have a 2 natural log of x minus 1. That's our antiderivative. We're done with the question. Partial fraction decomposition based on you correctly identifying those terms in the denominator. Hopefully that was helpful. Leave a comment down below, or check out my webpage. It's CalcCoach.com. Like and subscribe, as my daughter tells me I have to say at the end of every video. All right, take care. Bye-bye.